Hello there, and welcome. Tonight, we're reaching into the deep, dark before everything before time, space, stars, or gravity. There was no Earth, no galaxies, not even darkness, just a silence so vast it had no meaning. Yet, but from that silence, something stirred, a quantum flicker, a ripple of possibility. And in that moment, or something that wasn't even a moment, the universe began preparing to be born. What came before the Big Bang? Not myths, not guesses, but the deepest theories stitched from math, light, and time. Some are haunting, others feel like riddles written in gravity, and all of them ask a single quiet question: what lies beyond the beginning? And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or press the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. At the very edge of what we call time, there's a silence deeper than anything we've ever known. Not a silence like a quiet room or a forest at dusk, but a silence with no sound, no motion, no passage. Because before time began, there was no before. Not in the way we understand it. That word before breaks down, loses its meaning, slips through our fingers. We use time to measure everything: days, lives, the spin of galaxies. But if time itself had a beginning, then the idea of something happening earlier becomes a kind of illusion, a grammatical ghost, a habit of thought carried into a place where it doesn't belong. This is the edge of time, a boundary, not like a wall or a border, but like the edge of a shadow, soft, undefined, and not entirely real. We imagine the Big Bang as a kind of explosion, a fiery burst in space that started it all. But that picture is wrong. It wasn't an explosion in space, it was the expansion of space itself. And before that expansion, there was no space, no ticking clock, no stage on which anything could happen. Whatever may have existed beyond that moment didn't exist in time. It existed without it, if that's even the right word. We like to say things have causes, that one thing leads to another. But causality relies on time, on one moment following the next. Without time, cause and effect become tangled, or maybe meaningless. Some physicists suggest that time is not a fundamental part of the universe at all, that it's emergent, like waves on water, or weather in the sky rising out of deeper, timeless processes we can't yet see. If that's true, then the Big Bang wasn't the first tick of the universe's clock. It was the moment the clock began to tick. And yet, we keep asking, what came before? It's not just a scientific question, it's a human one. We're creatures of narrative. We look at any event and instinctively ask, what happened just before this? And what before that? It's how we make sense of life, of memory, of loss. But here, at the very beginning of beginnings, that question becomes a kind of mirror, showing us the limits of what we can know, or even ask. Still, scientists try, not because they expect a clear answer, but because the mystery itself is worth chasing. Some theories propose that the universe emerged from a quantum vacuum, a kind of roiling nothingness filled with virtual particles and fluctuations. In that view, nothing is never really empty. It's unstable, pregnant with potential, a quantum field bubbling with the possibility of becoming something more. But that too raises questions. If the vacuum existed before time, how did it fluctuate? And if it didn't, then how did it become unstable in the first place? Others imagine the Big Bang as a kind of transition, not from nothing to something, but from one state of reality to another. a cosmic phase change, like water freezing or boiling. In that view, the singularity isn't the beginning, but a threshold, a veil. And on the other side of that veil lies, what? Another universe, a different kind of space, a realm with no dimensions, no entropy, no direction. The truth is, we don't know, and we may never know, because our tools, mathematics, observation, logic, were built within time. They're shaped by the very fabric they're trying to see beyond. It's like trying to measure the edges of a dream while still dreaming. Even the idea of a singularity, a point of infinite density and zero volume, may be more of a placeholder than an actual thing, a symbol for where our theories break down, where general relativity and quantum mechanics stop agreeing. It's not just a hole in space, it's a hole in our understanding, a spot where the laws of physics themselves dissolve. And yet, from that moment, or that threshold, came everything. Space, time, matter, light, every star, every planet, every atom in your body. The laws of physics unfurled like the rules of a game that hadn't been invented until the first move was made. And here we are, 13.8 billion years later, trying to imagine what could possibly come before something that has no before. There's something oddly comforting in that. Not the mystery itself, but the silence it leaves behind, the humility it demands. For all our maps and equations and telescopes, the universe still holds secrets we cannot reach. Not because we haven't looked hard enough, but because some questions may lie outside the realm of answers, and still we ask them. Not because we expect to solve them tonight, but because there's beauty in the asking, in the edge itself, in the strange possibility that time, this thing we live and die inside, might be just one layer of reality, thin and temporary, like frost on glass. If time had a beginning, maybe it will also have an end. Maybe the universe will grow cold and quiet, and the ticking will stop. Or maybe time is a circle, folding back on itself. Maybe the end will touch the beginning, and we will find ourselves, somehow, back here at the edge. And if that happens, perhaps someone, somewhere, will ask again, what came before? Nothing is not what we think it is. We imagine it as a blank sheet, an empty room, a dark sky with no stars. But true nothingness isn't emptiness. It's the absence of even the possibility of something. No space to be empty, no time to pass, no laws to govern, no vacuum, no void. It's not quiet, it's not still, it's not black, it's not anything. And yet, somehow, we suspect that everything came from it. This is the problem of nothing, a puzzle that feels simple until you try to hold it. Then it slips, like trying to catch smoke in the dark. Physics wasn't built to describe nothing. It's a language written for things, particles, energy, forces, dimensions. But if the universe came from nothing, then nothing must be real in some sense. And if it's real, it must be describable. That's where the trouble begins. In classical terms, empty space is still something. It has dimensions, direction, and geometry. It can bend and ripple. It can contain light, radiation, dust. Even the quietest patch of vacuum is alive, with quantum fields, invisible grids stretching across the universe, vibrating with potential. In quantum mechanics, particles can appear out of this vacuum momentarily, borrowing energy from the uncertainty of nature before vanishing again. This vacuum is not nothing. It is a sea, restless even in its lowest energy state. A fabric that persists even when every stitch of matter is gone. So what do we mean when we say the universe came from nothing? Some physicists suggest that what we call nothing is actually a false vacuum, a temporary, unstable version of empty space that can decay into something more stable. That decay, they propose, might trigger the birth of a universe. Like water freezing into ice, it would be a transformation from one state to another, not a creation from absence. Others imagine a quantum fluctuation in a timeless void, a statistical burp in an eternal field of possibilities. In this view, our universe didn't arise from true nothingness, but from a kind of probabilistic haze, a background of potential, not absence. But that only shifts the question, where did the vacuum come from? Or the quantum fields? Or the possibility of fluctuation? If any of those existed before, then there was something, a structure, a law, a canvas, and we're back where we started. What makes this problem so strange is that we don't even know what kind of answer we're seeking. In science, we usually look for causes, mechanisms, patterns. But with nothing, there are no causes to trace, no mechanisms to test. The moment we describe it, we give it qualities. And if it has qualities, it isn't nothing. It's something pretending to be nothing. In philosophy, the question is even older. Why is there something rather than nothing? It's a question that sits at the root of all others. Some argue that nothingness is simpler, more natural. That existence is the real surprise. Others say that nothingness is unstable, or even impossible. That nothing was never a real option. That reality must exist, not because of a reason, but because of logic itself. Because the alternative can't sustain its own meaning. Some thinkers suggest that nothingness isn't just hard to imagine, it's impossible. That consciousness itself requires contrast. You can't think of nothing without thinking of something to compare it to. The mind flinches at the void and fills it with shadows. Silence becomes a hum. Blackness becomes a background. Even when we try to imagine a perfect absence, we do it with presence, aware, watching, existing. And maybe that's the key. Maybe the universe exists because it's the only way awareness can arise. And maybe once awareness exists, the idea of nothing becomes forever unreachable. A door that's closed not by force, but by fact. Because something is, this isn't just abstract. It matters because it frames everything else. If the universe came from nothing, it means that existence is not dependent on prior matter or energy, that the laws of physics might emerge from deeper principles. That reality could be spontaneous, uncaused, without precedent. And that would mean that we, too, are part of something more surprising than we ever imagined, a universe that didn't emerge from chaos or design, but from the impossible birth of being itself. Some theories go further. They propose that nothingness doesn't exist, not in any absolute sense. That at the deepest level, there is always something, some energy, some law, some pulse of being. That the very idea of nothing is a human construct, a placeholder for mystery. And that even if you erased everything, all galaxies, all particles, all fields, all dimensions, you'd still be left with the rules, with the logic, with the possibility of something beginning again. Other theories suggest we're asking the wrong question, that instead of asking why there is something, we should ask why this something, why these laws, these constants, this expansion, this silence. Maybe other kinds of somethings exist, other universes with different structures, and we are just one variation in an infinite landscape. In that view, the problem of nothing dissolves into a sea of possibilities, not a single beginning, but an unending field of becoming. But even in those grand theories, nothing haunts the edges, not as a presence, but as a possibility we can't quite erase. A kind of philosophical black hole. We circle it, define it, push it away, but it keeps pulling, a reminder that beneath everything we understand, there is still a question that resists answers. What is nothing? We don't know. We may never know. But in that question lies the first flicker of wonder, the first tension in the fabric, the first breath of a story that has no beginning. And in the quiet between stars, that question still lingers, soft, unanswered, and infinite. We think of time as a line, a single strand stretched from past to future, from memory to possibility. We imagine it ticking forward, second by second, like a soft metronome holding the rhythm of the universe. We age along it, plan by it. We name our lives in its increments, years, moments, histories. It feels absolute, like the background on which everything unfolds. But what if that's not how time really works? What if time isn't a river flowing from a source, but a pattern that rises from something deeper, something that doesn't flow at all? In the world of modern physics, time might not be as fundamental as it seems. It could be emergent like temperature, or color, a quality that appears only when enough things are in motion together. A collective property, not a basic ingredient. Just as a single molecule doesn't have a temperature until it's part of a crowd, time may not exist until matter and space begin to interact. If that's true, then time itself had to emerge, just like stars and gravity did. It wasn't always here. And if time is emergent, it means that before the Big Bang, time might not have been absent. It might not have been there at all. Not stopped, not paused, just undefined. No ticking clock, no forward direction, no sequence to follow. The word before becomes a kind of illusion, a word, shaped by the arrow we feel, but may not truly understand. Some theories suggest that in the early universe, space and time were so tightly wound together that they were interchangeable. Quantum geometry replaces the smooth continuum with something granular, a froth of probabilities where distances are smeared and durations lose meaning. In this view, time is not a line, but a phase, a feature that turns on when the universe becomes large and cool enough for classical behavior to take hold. Until then, everything is suspended in a haze of possibility. There's a theory called timeless physics. In it, the equations that describe the universe don't require time at all. They show relationships, connections, constraints, but no clock. Events are just configurations, different arrangements of energy and space, like frames in a reel of film with no projector to roll them forward. The motion we perceive might be our consciousness moving through those frames, giving the illusion of flow. And if time doesn't flow, then perhaps the past isn't gone, and the future isn't waiting. Perhaps all of time exists at once, a vast landscape, not a road. What we call now is just one point in that landscape, like a single town on an endless map. We travel through it by living, but the other places don't vanish. They simply remain, quiet and unreachable, except through memory or imagination. This idea is called the block universe. In it, every moment that ever was or ever will be is equally real. You at 5 years old, you tomorrow, you dreaming tonight or taking your last breath decades from now, all of them etched into the fabric of space-time, unmoving, already there. Time becomes a dimension like space, something we move through but do not create. It's not how we experience the world, but the universe is not required to feel familiar. Why, then, do we feel time moving forward? Why does entropy increase? Why do we remember the past, but not the future? The answer might lie in thermodynamics. Entropy, the measure of disorder, tends to increase. A broken glass stays shattered, not because it can't reassemble, but because there are far more disordered states than ordered ones. The arrow of time, as we feel it, may simply be the direction in which entropy grows. The universe started in a low entropy state. Every second that passes increases the number of possible arrangements, and that increase is what gives time its forward tilt. But this directionality is local, a product of where we are and what conditions we emerged from. In a different part of the cosmos, or under different rules, time might feel different, or not move at all. In the deep language of quantum gravity, time often disappears. The equations that describe black holes, or the first instant after the Big Bang, seem to work best when time is not assumed at all. Space twists and folds, energy loops into itself, and time becomes a shadow, not a presence, but a trace, not a river, but a ripple. If time can emerge, then so can its direction. its speed, its boundaries. Maybe some universes have two arrows of time moving in opposite directions. Maybe our own future is someone else's past. Maybe the Big Bang was not the beginning of time, but the middle, a fulcrum where two timelines unfold away from each other, mirrored and inverted, forever separate, forever entangled. And if time is not linear, then our place within it shifts. We are not just travelers from birth to death, pulled forward by an invisible thread. We are arrangements of matter and memory, shaped by entropy, suspended in a wider story where every chapter exists at once, a story with no first page and no final word, just an eternal unfolding, flickering in and out of awareness. We still build our lives around time. We still feel it pass. We still grieve what's lost and wait for what's next. But somewhere deep beneath that feeling, the structure may be different, more like music than mechanics, more like geometry than motion. Perhaps time is not what holds the universe together. Perhaps it is what the universe builds when it begins to notice itself. In the stillness before everything, there may have been a kind of nothing that wasn't entirely empty. Not the absolute void we imagine, but something stranger, a vacuum filled with potential, humming softly beneath the threshold of existence. This is the quantum vacuum, and in the language of physics, it's never truly silent. Even when space is stripped of all matter and energy, when temperature drops to absolute zero and every particle is erased, there remains a flicker, a tremble, a field of uncertainty that cannot be switched off. This isn't just theory. It's built into the very framework of the quantum world. A restless sea of fluctuations, where particles can blink into existence and vanish just as quickly, without warning, without cause. These quantum fluctuations are not like ripples on a pond, nor like the static on an old television. They are more fundamental tiny bursts of possibility governed by Heisenberg's uncertainty principle, which says that at the smallest scales, you can never know everything about a system. You can't know both where something is and how fast it's moving. You can't pin things down without them slipping away. The more precisely you try to measure one thing, the fuzzier everything else becomes. Reality, it turns out, is not made of absolutes. It's woven from probabilities. In that haze of probabilities, particles can emerge from the vacuum, hover for a moment, and vanish again, borrowing energy from the universe and returning it before anyone notices. These are called virtual particles. They're not stable, not observable in the ordinary sense, but their presence is real enough to exert pressure, to shift energy levels, even to create force. They live in the gaps between certainty, and they may be the key to why anything exists at all. Some physicists believe that the entire universe, all of space, time, and matter, may have emerged from a fluctuation like this, a spontaneous breach in the stillness, a tiny pocket of energy that swelled, unfolded, and became the cosmos. In this view, the universe didn't need a cause in the classical sense. It didn't explode out of an existing something. It blossomed from a state of pure potential, where the rules of quantum mechanics allowed for spontaneous creation. It sounds like magic, but it's grounded in mathematics. In quantum field theory, the vacuum is not an empty backdrop. It's an active player, a dynamic field with structure, rules, and energy. It's seething, invisible, omnipresent. And because the laws of quantum mechanics allow for fluctuations of energy to happen without a cause, so long as they don't last too long, it's possible that one such fluctuation grew unstable. It crossed a threshold, perhaps triggered by inflation, and gave rise to a universe, to this universe. And once it began, it grew. The early universe, dense and hot beyond imagination, may have undergone a period of rapid expansion known as cosmic inflation. This expansion would have smoothed out any irregularities, stretched quantum fluctuations into the seeds of galaxies, and created the vast, flat cosmos we observe today. But that initial spark, that first flicker of being, may have been nothing more than a quantum hiccup, a moment when probability collapsed into presence. This is not just poetic speculation. It's supported, in part, by the uniformity of the cosmic microwave background, the afterglow of the Big Bang. The tiny variations we see in that background, differences in temperature, density, and radiation, are exactly the kind we'd expect from quantum fluctuations stretched across space during inflation. In other words, the fingerprints of those early quantum tremors are still visible in the sky. But even here, the questions pile up. If our universe was born from a fluctuation, what was the field it fluctuated within? If quantum rules allowed for a sudden burst of energy, where did those rules come from? Were they always there, or did they too emerge with the birth of time and space? And if fluctuations can happen spontaneously, does that mean other universes are being born all the time in far-off corners we'll never see? Some theorists suggest that this isn't just possible, it's inevitable, that quantum fluctuations, given eternity, will eventually birth every possible configuration of reality, that universes are constantly blooming like soap bubbles in an endless foam. In that view, our universe is just one bubble among countless others. Some might collapse immediately, others might expand forever, each with its own physics, its own constants, its own rules. It's called the multiverse, and if it's real, then our universe might be not only temporary, but one among infinite variations, an echo in a vast chorus of being, a product not of design or necessity, but of chance. A universe born from a fluctuation, tuned just so, where stars can form, and atoms can bond, and consciousness can rise to ask what started it all. And yet, even the multiverse needs a canvas, a background, a set of conditions that allow fluctuations to happen in the first place, so we return to the same horizon. The quantum vacuum might explain how the universe appeared, but it doesn't explain why the vacuum itself exists, or why the laws of quantum mechanics hold it all. Still, the fact that something can come from almost nothing is staggering, that the quiet trembling of a quantum field could unfold into everything we see. Galaxies, oceans, trees, minds, is perhaps the most profound idea in modern science. It rewrites our understanding of creation. It suggests that the universe doesn't need a creator in the traditional sense, that it doesn't even need a cause, just the right conditions for uncertainty to play its game. In this picture, the Big Bang wasn't a singular act. It was a consequence, a ripple in a field that had no center, no direction, and no end. A spark in the dark that didn't just illuminate the void, it redefined what darkness meant. And so we find ourselves here, 13.8 billion years later, built from the dust of stars and the probabilities of fields, listening for echoes in the noise. And when we close our eyes at night, in the quiet between thoughts, we might catch a glimpse of that deeper stillness, not as absence, but as the birthplace of everything. A vacuum that was never truly empty, trembling with the possibility of us. Imagine a field not of grass or grain, but of energy, stretched infinitely across a realm beyond time. This field doesn't sit inside space, because it is space. Or rather, it's the potential for space to erupt. It's calm, but not still, smooth but not quiet. Beneath its surface, possibility stirs. And from this field, the universe, our universe, may have been born. Not as a singular explosion, but as a bubble. A delicate, expanding sphere that budded off a much larger, unending process. This is the idea of eternal inflation, and if it's true, then the Big Bang wasn't the beginning. It was just one spark in a fire that never goes out. In this theory, inflation, that rapid expansion that followed the Big Bang, isn't a one-time event. It's a self-replicating process, where space itself inflates faster than the speed of light, spawning new regions constantly. Most of these regions remain locked in inflation, stretching and stretching forever. But here and there, tiny patches fall out of that expansion, cool and settle. When that happens, a bubble universe forms. Ours is one of them. There could be countless more. Picture boiling water, The pot is the inflating field. The bubbles are universes. Each bubble forms, grows, and detaches, floating in a sea that continues to boil around them. In this cosmic version, the bubbles don't pop, they expand. Inside each one, a different universe takes shape. Some may look like ours, others could follow entirely alien laws. The constants of nature might shift. Gravity might behave strangely. Time might curve or loop or freeze. There could be no matter at all, or too much to form structure. Most would be inhospitable to life, but some, like ours, might find a narrow path where stars shine, atoms bond, and observers emerge to ask what it all means. This view reshapes our sense of scale. The observable universe, everything we can see, every galaxy, every particle, becomes a single room in a vast mansion with infinite halls. We live in one bubble, but the mansion is full of them, drifting apart faster than light can travel, unreachable, unknowable, each one with its own birth, its own physics, its own story. But here's where it gets stranger. Because inflation never stops, new universes are always being born. The process is eternal, both forward and backward. There's no first bubble, no ultimate origin. The field just is, like a sea without a shore. Even as old regions slow down and coalesce, new ones erupt into being. The multiverse, in this model, is not a collection of universes floating in pre-existing space. It is space itself, fragmenting and multiplying forever. And what lies between the bubbles? Nothing we could survive. The inflating space between them is colder than cold, thinner than vacuum, more alien than anything we know. If two bubbles ever collided, the result would be catastrophic. A wall of energy rushing in at nearly the speed of light, reshaping everything in its path. But the odds of collision are vanishingly small. Inflation pushes the bubbles apart faster than they could ever drift together. The space between is always growing, always stretching, always moving faster than any signal can cross. This theory isn't just abstract math. It makes predictions. The tiny variations in the cosmic microwave background, those speckles of temperature we see in every direction, are fingerprints left by quantum fluctuations during inflation. And while we haven't yet seen direct evidence of other bubbles, some researchers have proposed that scars from past collisions might show up as circular patterns in the sky. So far, no confirmed signs. But the search continues. Still, the real power of eternal inflation isn't just in the physics, it's in the perspective. It suggests that our universe, this place we call everything, may be a local event, a regional bloom in a much grander garden. It means that the laws we treat as universal may be provincial, that the constants we measure, the particles we catalog, the forces we map, are not written in stone across reality. They're just features of our own small patch. In another bubble, things might be utterly different, maybe even unimaginable. And if there are infinite bubbles, then every possible configuration of matter could exist somewhere. There could be other versions of Earth, other versions of you, not in the way science fiction often imagines, not clones or copies, but statistical twins, chance arrangements that, through sheer scale, eventually repeat. It's not about fate or design, it's about probability stretched across eternity. It also redefines what we mean by beginning. If the multiverse is eternal, then there was never a moment when it started. It didn't emerge from nothing. It just is a process without a first step, without a creator, without an edge. The question shifts from, why did the universe begin, to, why does this bubble have the features it does? And that, some argue, might be answered anthropically, because only bubbles with the right properties can host observers capable of asking the question. It's a humbling idea, but it's also liberating. It suggests that we are not the center, not the default, not the culmination of cosmic history. We are a flicker in a foam that never ends. And yet, within our flicker, we've built stories, cities, and languages. We've asked questions no bubble may ever answer, and we've looked into the dark and tried to name it. If eternal inflation is real, then we are forever surrounded by what we can't see. Universes being born while we sleep. Laws we'll never measure. Histories we'll never know. But here, in this bubble, we get to wonder. We get to imagine. And maybe that's enough to drift, wide-eyed, in the wake of a theory that tells us we were never alone. Somewhere, perhaps unimaginably, far beyond the edge of what we can see, there may be another universe, a place with its own stars, its own laws, its own strange sky, and farther still, another, and another, not scattered like islands across an ocean, but layered like pages in a book, or grown like branches from a common root. This is the multiverse, a concept that has drifted from theoretical margins into serious conversation. Not a single idea, but a family of possibilities, different ways in which the cosmos might be more vast, more diverse, and more surreal than anything we were taught to expect. The multiverse is not a science fiction fantasy born of wishful thinking. It is, in many ways, a consequence of physics taken seriously, followed to its logical extremes. Each version arises from a different question about quantum mechanics, cosmology, and mathematics. Together, they sketch a reality far stranger than the one we feel with our hands. In quantum mechanics, every event is governed by probabilities. A particle can be here or there, spinning one way or the other, with no definite outcome until it is measured. But what if the measurement doesn't collapse the wave of possibilities? What if instead, all outcomes happen each in its own branching world? This is the many worlds interpretation. It suggests that every quantum decision splits the universe. In one, you turned left. In another, you paused. In another, you never existed. These worlds don't interact. They unfurl in parallel, like silent threads in a tapestry too vast for any mind to hold. All possibilities, real somewhere, all paths, walked by someone. Then there's the cosmological multiverse, a direct offspring of eternal inflation. As inflation continues in far-off regions of space, new bubble universes keep forming. Each bubble might have different physical constants, different particle types, different geometries of space and time. Most may be sterile and stillborn, but some, like ours, bloom with complexity. This multiverse is spatial, each universe occupying its own bubble, eternally separated by inflating space. We cannot reach them, but their existence may be implied by the same math that explains our own. There's another kind, the mathematical universe hypothesis. This idea, proposed by cosmologist Max Tegmark, suggests that all mathematical structures exist as real universes, that every consistent set of equations corresponds to a physical reality. In this view, mathematics isn't just a tool for describing the world. It is the world. Every coherent framework, every self-consistent logic spawns a realm of existence. Somewhere, there's a universe where 2 + 2 = 5, not by mistake, but because that's how it's defined. It's not that math models reality. Reality is what math does. Some multiverse theories are even more conceptual. In string theory, the equations allow for a nearly infinite number of possible configurations of curled-up dimensions, tiny shapes that determine the nature of forces and particles. Each configuration is like a different setting on a cosmic dial. If string theory is correct, then our universe is one solution among many, like a particular chord struck in a symphony that plays forever. And the other, chords, they may be real places too. And then, there are the black hole universes. Some theories suggest that every black hole is a kind of portal, not to another part of our own universe, but to an entirely new one. That the singularity at the center isn't the end of space-time, but a beginning. That when matter collapses beyond the event horizon, it seeds a new cosmos, sealed off from ours but growing from our debris. If so, every galaxy could be spawning new universes in secret, hidden behind curtains of gravity. Each of these ideas is extraordinary. and each opens a door to countless beginnings, not just one big bang, but a garden of them, blooming in different directions, governed by different rules. Time may begin in one and loop in another. Matter might never form in some, or never stop collapsing in others. The multiverse transforms our universe from the totality of everything into a local occurrence, one blossom among infinite arrangements shaped by chance or necessity or both. But if the multiverse is real, what does that mean for us, for our choices, our memories, our place in the scheme of things? It might mean that everything that can happen does happen, that every choice we don't make is still made somewhere, that versions of us similar but not the same walk other paths, love other people, mourn other losses. These aren't shadows or illusions. In some interpretations, they are as real as we are, just out of reach, forever partitioned by the structure of reality. It's an unsettling thought, but also a kind of solace, that nothing is truly lost, that every outcome has its place, that we are part of a deeper tapestry than we can ever fully trace. Of course, not all physicists agree. The multiverse by its nature is hard to test. It makes bold predictions, but many lie beyond the reach of current instruments. Some critics argue that a theory that cannot be falsified is not truly scientific. Others counter that science must follow where logic and evidence lead, even into unobservable realms. The debate continues, as it should, but even without proof, the idea has power. It changes how we see the cosmos, not as a lone miracle, but as one flowering of possibility among many. It stretches our imagination beyond the familiar. It invites humility and awe. Somewhere, perhaps, another you is looking up at another sky, asking the same questions, feeling the same strange wonder. Not in metaphor, but in fact. Not in fiction, but in physics. And perhaps that's what matters most, that we can ask it all. That in this universe, this bubble, this branch, this thread, we have minds that can imagine beyond its walls, that we can listen into the silence and wonder if it goes on forever. In the dark beyond memory, before galaxies stretched their arms and stars whispered into being, there may have been another universe. Not ours, but something that came before. A cosmos that bloomed, aged, and folded in on itself like breath exhaled. And from its ashes, something stirred again. A swelling, a crackle, a pulse. The Big Bang not as a singular beginning, but as a transition. The latest note in a symphony that never truly started and may never end. This is the idea of the cyclic universe, where time loops not in circles, but in spirals, each pass reshaping the cosmos, again and again. The concept is older than modern science. Ancient mythologies imagined time as a wheel, the heavens born and destroyed in endless succession. But now, physics offers versions of that story rooted in mathematics and observation. One version suggests that the universe expands for billions of years, then slows, halts, and begins to contract. Galaxies drift closer, space shrinks, stars collide and crumble. Eventually, all matter collapses inward until the universe becomes a single point, dense, hot, and ready to begin again. A big crunch, followed by another big bang. But our current universe isn't showing signs of slowing down. Quite the opposite. Observations suggest that expansion is accelerating, driven by a mysterious force we call dark energy. This seems to rule out the idea of a simple contraction. Yet, theories evolve. One model, known as the ekpyrotic universe, suggests that our cosmos is one of two branes, vast, membrane-like structures floating in a higher dimensional space. When these branes collide, they release energy, triggering a big bang. Then they separate, and after eons of drifting, they collide again. Each collision gives birth to a new universe, and the cycle continues, not through contraction, but through rhythm. A cosmic heartbeat hidden beyond dimensions. Another proposal comes from conformal cyclic cosmology, a model by physicist Roger Penrose. It suggests that as the universe expands and ages, black holes slowly evaporate, stars burn out, and particles lose distinction. Eventually, everything becomes smooth and featureless, no clocks, no mass, no structure. In this final state, time loses meaning, and in that timelessness, Penrose argues, the universe can be rescaled, stretched into a new beginning. The end of one cosmic era becomes the seed of the next, a phoenix, not rising from flame, but from mathematical elegance. What unites these theories is the idea that the universe is not a one-time event, not a fluke, not an exception, but a chapter in a larger story. Each cycle inherits something from the last, perhaps not matter, but patterns, structures, or subtle imprints. The cosmic microwave background, that faint radiation still whispering across the sky, may hold echoes from a previous eon. Rings of anomalous temperature, strange alignments. Some physicists believe they are the fingerprints of universes before ours. Faint scars left behind when something vast collapsed and something new ignited. If this is true, it changes how we think about origin. The Big Bang, often imagined as a sudden explosion from nothing, becomes a transformation, one phase flowing into another. The laws of physics aren't randomly set, but shaped by cycles of trial and refinement. The constants of nature aren't imposed from outside, but inherited, like memory passed down through time. Even the asymmetries of our universe, why there's more matter than antimatter, why time flows in one direction might be explained by what came before. It also shifts how we think about fate. If the universe is cyclic, then everything is temporary. Stars are born, die, and return as stardust. Galaxies drift, collide, and vanish, and entire universes too may fade and return endlessly. This isn't a cycle we can witness from inside. It unfolds over billions, trillions, even infinite spans. We are like mayflies in a storm that circles the earth, aware only of our moment, but part of something far larger. But the cyclic universe raises difficult questions. What survives from one cycle to the next? If matter is destroyed, do any structures persist? Are there universal truths that carry across, bounces laws, patterns, blueprints for galaxies? Could consciousness, in some strange form, recur? And are the cycles identical, or do they diverge like echoes fading into distance? Some models suggest that entropy resets, that the disorder of the old universe is erased or transformed. Others suggest that each cycle grows longer, more complex, like ripples spreading across a pond. There may be a memory, of sorts, etched into the fabric of reality, a kind of ancestral physics, growing more refined with each iteration. Or perhaps each universe is completely new, a blank canvas, unaware of the masterpiece it follows. In our cycle, we find ourselves in a moment of immense expansion. Stars are being born, black holes are feeding. Consciousness has risen on at least one blue planet, looking up and asking how it all began. But if this isn't the first time, then it may not be the last. Somewhere, impossibly far ahead, everything we know may collapse or dissolve, and something else, something unimaginable, will take its place. And yet, that doesn't diminish this moment. It deepens it. Because even if this is just one beat in an endless rhythm, it's a beat we get to feel. We are the eyes and ears of a universe learning to remember, to tell its own story, to wonder if it has told it before. If the universe is cyclic, then we are part of a dance that has no true beginning and no final end. A waltz of creation and collapse, of silence and song. And perhaps, in the hush between cycles, in that breathless pause before another bang, something lingers, not matter, not light, but the potential to become, again and again. Imagine the universe, everything we've ever known, every atom, every galaxy stretched like a sheet, thin, vast, and gently rippling, like the surface of a pond on a still morning. But this sheet doesn't float in emptiness. It hovers in a higher dimensional sea, unseen and silent, carrying us along through time. In the language of string theory, this sheet is called a brane, short for membrane. And in some versions of the theory, our universe is just one brane among many, adrift in a deeper space we cannot touch. Brane cosmology invites us to step beyond the familiar three dimensions of space and one of time. It suggests that there may be more not as metaphor, but as literal directions curled up or hidden from view. Just as a two-dimensional creature living on a flat surface would be unaware of the third dimension above and below, we too may be confined to our brane, blind to the bulk space that surrounds us. This bulk, sometimes called the higher dimensional bulk, or simply the bulk, is not empty. It can carry gravity, energy, and perhaps even other branes, entire universes parallel to ours, just out of reach. In this framework, the particles that make up you and me, electrons, quarks, photons, are vibrations of tiny strings pinned to our brane. They cannot leave. They are stuck, like raindrops sliding along a sheet of glass, unable to fall through. But gravity is different. It is the one force that might leak into the bulk. This could explain why gravity is so much weaker than the other forces, not because it's inherently feeble, but because it's diluted, spreading out across dimensions we cannot see. The tug we feel from a distant star may be just a whisper, the echo of a stronger force bleeding into other realms. Some versions of brane cosmology go further. They suggest that the Big Bang itself was not the origin of everything, but the result of a collision. Two branes, drifting through the bulk, may have slammed into each other, releasing immense energy and setting off the hot, dense expansion we call the birth of the universe. In this view, the Big Bang wasn't a beginning, but a moment of contact, a crash between dimensions that reshaped the fabric of reality. What's even more provocative is that this might not have been the only time. Branes could drift apart and then collide again, over and over, in a slow cosmic rhythm. Each impact would be a new beginning, a new universe blossoming from the energy of interdimensional contact. We may live in one cycle of many, each born from the dance of branes through a timeless sea. These ideas are hard to picture. Our minds are built to imagine space as length, width, and height, a box we move through, not a flexible surface embedded in something more. But math allows us to explore beyond intuition. Equations trace the contours of spaces with 10 or 11 dimensions, and string theory is one of the few frameworks that holds together at the quantum level and includes gravity. It's an ambitious attempt to unify all forces under a single, elegant structure. And in that structure, branes are not exotic outliers. They are natural solutions. If our universe is a brane, it may have neighbors, other branes, perhaps just a fraction of a millimeter away in the bulk, unimaginably close, yet utterly unreachable. Each could host its own version of physics, its own laws, its own stars. They might be teeming with matter or utterly empty. They might be older than ours, or just beginning. They might never know we exist. Or maybe, through gravity or some other yet undiscovered interaction, there are subtle threads connecting us. There are even speculative ideas that dark matter, the invisible substance shaping galaxies, could be the shadow of particles from another brane, not from our world, but near enough to tug at us through the bulk, like neighbors we can't see but sometimes hear, tapping lightly through the walls of reality. Brane cosmology doesn't ask us to discard the universe we know. It simply invites us to imagine that it's part of something larger, that what we call the cosmos is not the whole, but a slice, a floating membrane stretched across dimensions, shaped by deeper laws. It also invites a new kind of humility. We once thought Earth was the center of everything. Then we learned it orbited the sun, which was one star among billions, in one galaxy among trillions. And now, even our entire universe may be a surface, a moving, rippling skin in a higher dimensional realm, But far from making us insignificant, this perspective shows how far our minds have reached. From cave walls to quantum strings, from sunrise myths to multidimensional brains, we have stretched our understanding into places no eye has seen. We have turned math into vision, and vision into awe. Maybe, someday, we'll find a way to test these ideas, to glimpse the imprint of another brain, to hear the faint music of higher dimensions, vibrating just beyond the veil. Or maybe we never will. Maybe the bulk is forever hidden, and brain cosmology will remain a beautiful theory, unprovable yet hauntingly plausible. Either way, the thought lingers, that we are part of a surface in motion, that the universe is not a solitary sphere, but a living sheet, floating, flexing, and perhaps one day touching something else. And when it does, a new spark may fly, a new story may begin. One more echo in the grand, silent fold of dimensions we cannot see, but which may hold the keys to all beginnings. Before time as we know it, before light had ever flared, there may have been two vast sheets of reality, ancient, silent, drifting. Not stars, not space, not even atoms, just brains, immense and empty, suspended in a higher dimensional void. They moved slowly, drawn together by forces older than motion itself. And then, with no witness but the void, they collided. That collision may have been our beginning, a crash so powerful it forged every particle, every field, every law we live by. This is the idea behind ekpyrotic cosmology, a vision of the universe born not from nothing, but from impact. Unlike the traditional Big Bang, which suggests the universe sprang from a singular point of infinite density, the ekpyrotic model offers a different origin story, one rooted in the physics of string theory and extra dimensions. It proposes that our universe is a three-dimensional brain embedded in a higher dimensional bulk, and that the Big Bang was the result of our brain slamming into another. That moment of contact didn't happen in empty space. It created space itself. It didn't happen in time. It created the very flow of time we now inhabit. To us, the collision would appear as a sudden, all-encompassing explosion, but in the ekpyrotic view, it was less like a firework and more like a hammer blow against a drumhead. The strike sent vibrations cascading through our brain, shaping its structure, setting it into motion. The energy released during the impact became matter and radiation. Space began to stretch, and time began to tick. But this idea doesn't just replace one story with another. It reframes the entire narrative. It means the universe wasn't a fluke, a one-time event rising from randomness, but part of a cycle. Because after that colossal crash, the brains didn't disintegrate. They rebounded, drifted apart, and slowly, ever so slowly, began to approach each other again. In the ekpyrotic model, this cycle repeats endlessly. Brains move closer. They collide. A universe is born. It expands and cools. Structures form stars, galaxies, people. And then, over incomprehensible spans of time, the brains drift apart and prepare to meet again. Each universe becomes a moment in a rhythm older than matter, a breath in a cosmic lung. This version of cosmology is deeply appealing to some physicists because it avoids the singularities that trouble other theories. It suggests that the universe never reaches infinite density or temperature. Instead, the collision is finite, controlled, and governed by known physical laws. And it offers a possible explanation for the uniformity of our universe, why the cosmic microwave background is so smooth, why the large-scale structure of space is so coherent. Those qualities could be the lingering echoes of collisions past. But perhaps the most profound implication is that we are not the first, that our universe, with its galaxies, its black holes, its fleeting minds, is just one note in a symphony of collisions. Each beat gives rise to a new cosmos. Each cosmos blooms with its own history. And after each expansion, a quiet return. Not an ending, but a retreat before the next impact. If this is true, then the silence between universes is not death, it is gestation, a long and patient waiting for contact. We live in the aftermath of one such collision. Everything we see, every mountain, every planet, every cell, is part of the debris still unfolding from that moment. The matter in your bones was once part of a wave of energy, coursing through a freshly born brain, and the vacuum between stars still hums faintly with the aftershock of that ancient impact. It's difficult to test such a theory directly. The collision happened before conventional time, and its traces are faint. But some cosmologists believe that subtle patterns in the cosmic microwave background, slight asymmetries, unexpected alignments, could be fingerprints of that primal event. Others suggest that gravitational waves, rippling through space like echoes through water, might carry the memory of impact. There is beauty in this vision, and something unsettling too. Because if universes are born from collisions, then reality is not stable. It is dynamic, restless. The space we inhabit is not fixed, but a phase in a deeper process we can barely glimpse. And it means that far beyond our stars, beyond the horizon of what we can ever see, another brain is out there, waiting, moving, approaching. Maybe in 1 trillion years, or 10 trillion, it will touch us again. Another spark, another creation, a new history, written in fire and cooled by time. And maybe, just maybe, in that distant cycle, something will remember. A pattern, a law, a whisper of what came before, a trace of us, folded into the next unfolding. In the stillness beyond imagination, deep within a universe that may not be our own, a star collapses. It folds in on itself, crushed by its own weight, until its mass becomes a singularity, a point of infinite density, where gravity reigns so absolutely that not even light can escape. We call it a black hole, and we think of it as an ending, the end of a star, the end of information, the end of space as we understand it. But what if it's also a beginning? What if, on the other side of that collapse, something expands, not into our universe, but into a new one? This is the idea behind black hole genesis, a radical, elegant, and haunting proposal. That every black hole could be a one-way tunnel to a black baby universe, sealed off from ours but expanding in its own private space-time, and that our universe, too, may have been born this way not from nothing, but from a death in a parent cosmos we'll never see. The logic is strange, but not impossible. When a black hole forms, it creates a horizon, a point of no return. To an outside observer, matter falling in appears to slow, asymptotically approaching the horizon forever. But for the matter itself, time continues. It crosses the threshold and collapses toward the singularity. And in that descent, something curious happens in certain models of general relativity. The geometry of space-time doesn't necessarily terminate. It can curve and pinch and re-expand, like a throat leading to a new region of space. A white hole, in this case, might not be a symmetrical twin to the black hole, spewing out everything it once consumed. It might be the first moment of a new universe, a big bang, seeded by the collapse of another. From the inside, this new universe wouldn't see the black hole as its origin. It would simply see an expanding cosmos, filled with energy, obeying its own physical laws. Time would begin at the bang, and space would grow outward. Galaxies would eventually form, stars would ignite, and life perhaps would open its eyes, never knowing its world was born from the death of a star in some distant, unreachable elsewhere. Our own Big Bang has always defied full explanation. The equations that govern it break down at the singularity, the point where space and time seem to come from nowhere. But if that singularity is the exit of a black hole in another universe, the paradox changes shape. Instead of asking how something came from nothing, we ask what kind of star collapsed to make us. What kind of parent reality folded inward so deeply that it punched a hole through space-time and gave rise to ours? It's not just poetic. The math, in some theories, allows it. Loop quantum gravity, a framework that attempts to unify Einstein's relativity with quantum mechanics, proposes that singularities aren't infinitely dense. Instead, space-time has a smallest possible scale, a kind of granular structure that resists absolute collapse. When gravity pulls everything together, quantum pressure pushes back. Instead of a singularity, you get a bounce. And on the far side of that bounce, a new region of space can unfold. If black holes can give birth to universes, then the cosmos is not a tree with one trunk, but a forest. Each black hole becomes a seed, and each seed grows its own space-time. Our universe could be just one branch on a colossal fractal, a multiverse where each universe spawns others through the life cycle of stars. Each one may carry different physical constants, different strengths of gravity, different rules entirely, and yet all of them trace their lineage back through death. Some theorists have even suggested this could be a kind of cosmic evolution. Universes that produce stars, and thus black holes, give rise to more baby universes. Those that don't, vanish. Over time, a natural selection of universes occurs, favoring those with the right ingredients for star formation, black hole production, and generational propagation. In this view, the laws of physics are not arbitrary. They are inherited, but we cannot see through the horizon. If other universes lie within black holes, they are forever sealed off from our view. We can't follow matter across the threshold, nor can we receive messages back. The membrane between worlds is absolute. And yet, the idea persists, haunting the edge of cosmology like a forgotten door. It invites a strange kind of reverence, that somewhere, in a universe long gone cold, a black hole still spins a grave in one world, a cradle in another, that the energy of collapse becomes the fire of creation, that what dies in one place may be born anew in another, forever hidden, forever separate, yet intimately linked. And it invites a question so vast it almost slips through the mind. If our universe came from a black hole, what came before that? How many generations back does this tree of creation extend? What primal universe birthed the first black hole, the first expansion, the first flicker of light? We may never know. But if the idea holds, then every black hole we observe, each shadow in the heart of a galaxy, is more than a mystery. It is a womb, and the stars that fall into it, the matter that vanishes without a trace, may be writing the first chapters of stories we'll never read. Stories of new beginnings, written in the language of collapse. In your quietest moments, when the world softens around you and the ticking of time feels unusually loud, you might notice something strange. Not about the clock itself, or the aging of your hands, or even the slow shifting of stars overhead, but about direction. About why time, of all things, only seems to move forward. Milk swirls into coffee, never the other way. Smoke rises, never descends, and reforms into wood. The past is known, the future is not. We live on a one-way street. This flow, this asymmetry is known as the arrow of time, and it is one of the deepest, most persistent riddles in physics. The strange thing is, the fundamental laws of nature don't actually care about direction. At the level of particles and forces, equations work just as well forwards as they do backwards. A film of two particles colliding, then separating, could be played in reverse, and the math would stay valid. But in the world we live in, the macroscopic, warm, chaotic world, time refuses to rewind. It moves with insistence, irreversible, irrevocable. So why? One possible answer lies in entropy, a concept from thermodynamics, the study of heat and energy. Entropy is often described as disorder, but more accurately, it's a measure of how many possible ways a system can be arranged without changing its overall state. A messy room has more entropy than a tidy one. A shattered glass holds more configurations than a pristine whole one. And the second law of thermodynamics tells us that entropy tends to increase over time, not because it must, but but because there are far more ways for things to be disordered than ordered. So the natural tendency of the universe is to move from low entropy to high, from order to chaos, from structure to scatter. This, many physicists believe, is the engine behind the arrow of time. Not the ticking of clocks, but the tendency toward disorder. The universe expands, entropy rises, and we are carried forward like leaves in a widening stream. But this raises a deeper question. If high entropy is the norm, then why did the universe start in such a low entropy state to begin with? The Big Bang, that hot, dense beginning, was incredibly uniform, smooth, ordered, improbably balanced. It was a rare state in a cosmos full of more likely chaos. Why start the story at such an unlikely beginning? No one fully knows. Some think it was just a random fluctuation. Others suggest a deeper law of initial conditions. But one thing is clear, the arrow of time is tied to that moment. It was the asymmetry of the beginning that gave rise to all other asymmetries, to memory, causality, experience. Without a past to contrast against the future, there would be no direction at all. And yet, there are places, even in theory, where this arrow might falter. Deep inside black holes, where time and space twist together in ways we barely understand, or near the edges of the universe, where cosmic expansion stretches everything so thin that direction begins to blur. Some models even suggest that at the far end of time, entropy might begin to reverse that. After reaching a maximum, the cosmos might contract, and the arrow could flip. Time, in that inverted world, would run backwards from our perspective. The future would become the past. Death might unspool into life, a kind of cosmic, palindromic loop. More radically, some physicists propose a time-symmetric universe, one where the Big Bang wasn't the start of time, but the midpoint. On either side, two universes unfold, each with its own arrow, pointing away from the bang. In that picture, we are the mirror of another reality, moving in the opposite direction. To them, we are the ones moving backward, but we can't see that universe. We are trapped in ours, with time pulling us forward relentlessly. Our memories are of the past, never the future. Our choices unfold in one direction, and no matter how deeply we understand entropy, no matter how precise the equations, we cannot walk backward through the door once it is closed. And yet, time's arrow is not always as rigid as it feels. In the quantum realm, where particles flirt with uncertainty and probabilities reign, events can become smeared neither fully past nor future. There, the difference between cause and effect can blur. Some interpretations of quantum mechanics suggest that future measurements can influence past states. Others argue that time itself may be emergent, not fundamental, but a result of deeper, timeless laws. If that's true, then the arrow we feel so strongly might be more illusion than rule. A pattern our minds impose on the dance of energy and matter. We remember the past because it's where entropy was lower. We forget the future because it hasn't yet spilled into complexity. We are creatures of thermodynamic bias, riding a current we cannot escape, not because time is flowing, but because we are. Still, the arrow defines us. It is stitched into every breath, every sunset, every fossil buried in the rock. It gives structure to stories, to history, to grief and hope. Without it, there would be no rhythm, no anticipation, no meaning in progress, just a featureless sea of possibilities with no direction to swim. So we keep moving forward, step by irreversible step. Even if time itself is an illusion, the arrow holds, because we live inside it, because we are made of it, because to be conscious, to be human, is to watch the present slip constantly into the past, never to return, and to feel that loss like a wind always at our back. At the supposed beginning of everything, where time frays and space collapses into silence, something extraordinary may have happened, or rather, not happened. Instead of an infinite wall where physics breaks and everything vanishes into a singularity, There may have been a bounce, a cosmic inhale before the breath we now live in. A shrinking universe, collapsing under its own weight, did not die in a final blaze, but rebounded. And from that moment of reversal, our own universe was born, expanding outward from the ashes of a prior world. This is the heart of a theory known as loop quantum gravity, and in it, the Big Bang was not the beginning. It was a transition. To understand this idea, you must imagine space itself not as a smooth, continuous fabric, but as something grainy stitched from loops, woven like a net. At scales trillions of times smaller than a proton, space may not be a liquid flow, but a lattice, a trembling scaffolding of quantum threads. These loops are not in space, they are space. The framework of reality is no longer infinitely divisible. It has texture, grain, a smallest possible unit, and when you try to squeeze this fabric beyond that limit, as gravity does at the heart of a collapsing universe, something changes. The theory proposes that before our universe began to expand, there was another universe, vast and full, that had been contracting for an unimaginable length of time. Galaxies moved closer, stars burned out, matter compacted. As this previous cosmos grew denser and hotter, space itself strained under the pressure. In classical physics, that collapse would end in a singularity, a point of zero volume and infinite density, where the laws of nature fail. But loop quantum gravity offers another path. At the smallest scale, quantum geometry resists compression. The loops that form space push back. They become stiff, unable to compress further. And then, like a spring coiled too tightly, the universe rebounds. That moment, the bounce becomes the bridge. On one side, a universe in collapse. On the other, a universe in bloom. This model is elegant because it avoids infinities. Infinities are signs of breakdown in physics, signals that our tools no longer work. A theory that replaces a singularity with a bounce restores continuity. It also opens the door to something profound, a cosmic history with no absolute beginning, a chain of universes, each one collapsing and giving rise to the next, stretching backward into a past we can barely imagine, and forward into futures we'll never see. In this view, time never truly begins. It curves. The bounce doesn't just offer a new origin story. It also provides a framework for explaining some of the mysteries in our current universe. The smoothness of the cosmic microwave background, the flatness of space. These are features that, in standard models, require special initial conditions or inflationary mechanisms to explain. But in the loop quantum bounce, they could be natural consequences of the physics near the transition. The contracting universe would have had time to smooth itself out before rebounding, erasing irregularities, and setting the stage for what came next. Still, the evidence is subtle. The traces of a prior universe, if they exist at all, would be faint, woven into the structure of the cosmos in ways we are only beginning to look for. Some theorists speculate that quantum imprints might linger in gravitational waves or in the polarization patterns of ancient light. Others think the bounce may have left scars in the distribution of galaxies, like echoes from another world, whispering through ours. But even if we never detect them, the idea leaves an imprint on our minds. It reframes death as transformation. It paints the universe not as a fragile spark from nowhere, but as part of a great rhythm, breathing in and out across eternities. Collapse is not a failure. It is preparation. The end of one cosmos becomes the seed of the next. And somewhere beyond our visible sky, perhaps even now, another universe may be collapsing inward, gathering momentum for its own leap into being. There is humility in this vision. We are not perched on the edge of a singular miracle, but flowing within a stream of cosmic cycles. Our laws, our particles, our stars, they may carry the fingerprints of a previous age, not reincarnation in the spiritual sense, but continuity in the deepest fabric of space and time. a universe that remembers not through memory, but through structure. And there is beauty too, in a cosmos where beginnings are never final and endings never absolute, where every expansion is a recovery from collapse, where creation is not a singular act, but a perpetual dance, bound by the laws of quantum geometry and the insistence of existence itself. So, when you look up at the night sky, you are not seeing the first act. You are looking at a moment in a much older story, one that may have no beginning, only transitions. Our universe may be a survivor, a child of collapse, born not in stillness, but in a rebound of impossible energy, rising from a geometry that refused to disappear. And perhaps, far into the future, we too will fall inward. We will grow quiet, we will compress, and space will resist. And again, the universe will bounce. In the deep cold of a timeless void, before seconds ticked and stars flared, there may have been no beginning in the way we imagine beginnings. No flash, no bang, no edge to cross or wall to burst through. Instead, something much quieter, a smoothing out, a soft unfolding, a silence that never broke, because there was never truly a moment before. This was the idea that Stephen Hawking once offered, a reimagining of time itself, not as a line with a sharp start, but as something curved and finite, like the surface of the Earth. Just as there is no edge where the planet begins, Hawking proposed there may be no singular instant when time switched on. Instead, what we think of as the beginning may have been a transition, one that took place not in ordinary time, but in something more elusive and strange, imaginary time. Imaginary time is not a fantasy or illusion. In mathematics, it's as real as any number, except it involves the square root of -1. Multiply time by this curious number, and you rotate it out of the familiar axis of past and future into a perpendicular direction. It becomes something space-like, something that behaves more like a dimension of space than like the ticking we associate with clocks or aging or memory. And when Hawking applied this tool to cosmology, something astonishing happened. The singularity, the theoretical point of infinite density and temperature, where the Big Bang is said to have begun, vanished. In its place, there emerged a smooth geometry, a rounded dome, finite but without edges, where the concept of before simply doesn't exist. It's not that the universe appeared from nothing, it's that the question of a beginning dissolves in the way a North Pole dissolves into lines of latitude. You can keep walking north until you reach the top, but there's no sharp point where north ends. The pole is not a place but a limit. So too, in imaginary time, the beginning of the universe may not be a point of origin, but a smooth cap in a deeper landscape we can't quite see. In this model, time is not fundamental at the earliest moments. It emerges only after a certain threshold, like steam condensing from water vapor as the air cools. Before that, time as we know it doesn't exist. There is geometry, there is possibility, but there is no ticking, no sequence, and this has profound implications. It means asking, what happened before the Big Bang, is like asking, what's north of the North Pole? It's a question that presumes a framework that doesn't apply. This concept doesn't replace the Big Bang, it reframes it. The expansion of the universe still happened, space still stretched, galaxies still formed, stars still lit, and we still emerged to ask questions. But the start of all this wasn't a break in physics, it was the softest of beginnings, rooted in deep quantum geometry, rounded like a sphere instead of cracked open like an explosion. Hawking arrived at this idea not alone, but in collaboration with physicist James Hartle. Together, they formulated what became known as the no-boundary proposal. It imagines the universe as a four-dimensional surface with no boundaries in space or time. You could travel in imaginary time across this surface and never hit a wall or edge, just like you can circumnavigate a globe endlessly without falling off. The boundary we thought was the beginning? It's not there. Just smooth curvature, just possibility folding into presence. Imaginary time allowed Hawking to use the machinery of quantum mechanics to describe the universe as a whole. In this model, the laws of physics don't just govern what happens inside the universe. They explain why the universe itself exists. And crucially, this approach helps sidestep the troubling infinities that plague other models. The same infinities that hint our understanding is breaking down. The no-boundary condition erases the singularity, not by denying the Big Bang, but by revealing a richer backdrop behind it. Of course, we don't experience imaginary time in daily life. To us, time marches forward relentlessly. But if imaginary time underlies the foundation of reality, it could explain why our universe emerged in a particular way, why it has the laws it does, the structure it does, the arrow of time we live by. From the smooth curves of this deeper geometry, a universe could blossom with logic and light. Entropy would increase. Stars would form. Life would awaken and wonder. The haunting beauty of this model lies in its humility. It doesn't claim a cause or demand a creator in the traditional sense. It suggests that the universe may be self-contained, complete, that the rules which allowed for its existence also determined its shape, and that nothing outside it needed to nudge it into motion. The universe simply is because it can be. And yet, there's something poetic in the way Hawking's vision preserves mystery. Imaginary time is not intuitive. It slips past the reach of our senses, humming beneath the skin of reality like a buried rhythm. Even Hawking, who helped give it form, acknowledged that we may never directly observe it. But its consequences could be imprinted in the cosmos, in the patterns of primordial light, in the distribution of galaxies, in the fine structure of space itself. Maybe one day we'll find evidence that supports this view, or maybe it will remain one of the most elegant ideas we've ever imagined, floating at the edge of understanding. Either way, the question of beginnings will never be quite the same, because in Hawking's universe, time didn't erupt from nothing. It rose gently, like mist from a still sea. There was no bang, only emergence, only unfolding. And in that quiet geometry, we might finally glimpse the truth that the universe doesn't need a spark to exist. It only needs the space to curve. Imagine for a moment that everything you see, touch, and remember your body, the stars, the oceans, and cities, the feel of your breath in the cool night is not as it seems, that the depth of your surroundings, the three-dimensional sweep of your life, is a kind of illusion, not fake, but emergent, like a shadow cast from a different shape, projected onto a world that feels solid. This is the strange possibility at the heart of one of the most mind-bending ideas in physics, the holographic universe. It began with a paradox. When black holes were first seriously studied, they brought with them a mystery so deep it shook the foundations of physics. According to classical ideas, if you toss something into a black hole, a book, a star, a person, it disappears beyond the event horizon, leaving behind only mass, charge, and spin. All the fine details, all the complexity of the fallen object seemed to vanish. But that raised a problem. In quantum mechanics, information cannot be destroyed. Even if you burn a book, its information is theoretically preserved in the ash, smoke, and heat it releases. But a black hole appeared to break that rule. Then came a discovery that changed everything. In the 1,970 seconds, Stephen Hawking showed that black holes aren't truly black. They emit radiation due to quantum effects at the event horizon. Over time, they evaporate. And if they disappear entirely, the information that fell into them seems to be lost forever. This conflict between relativity and quantum mechanics became known as the black hole information paradox. To resolve it, physicists began to rethink what space, and even reality, might be. One of the most important insights came from a physicist named Jacob Bekenstein. He found that the maximum amount of information or entropy that can exist inside a black hole is not proportional to its volume, as you might expect, but to the surface area of its event horizon. In other words, the information inside is somehow encoded on the outer shell, not within, but on the boundary. This was the first whisper of the holographic principle. Years later, building on this foundation, Juan Maldacena proposed something staggering. In a specific kind of universe, one with negative curvature, not quite like our own, but close enough to suggest parallels, there could be two entirely equivalent descriptions of reality. One would be a familiar universe with gravity, operating in 3 spatial dimensions and 1 of time. The other would be a quantum field theory without gravity, living entirely on the lower dimensional boundary, a sort of cosmic skin. Every object, every event, every interaction in the higher dimensional universe could be fully described by equations living on the boundary. It's like a hologram, a flat, 2-dimensional surface storing the information needed to project a seemingly 3D image. The world we move through, with its up and down, its inside and outside, may arise from data encoded elsewhere. And if this is true, then perhaps our entire universe is a projection. The implications are profound. It could mean that gravity itself, the most familiar force, the one that keeps our feet on the ground and the planets in motion, is not fundamental, but emergent, a ripple, a pattern that arises from deeper rules, etched onto a surface we cannot directly perceive. It challenges our intuitions about space and matter. It suggests that the universe may be more like a computation, unfolding according to rules inscribed on a distant edge. But what, then, lies beyond the projection? If our 3-dimensional universe is like the image on a screen, then perhaps the screen itself, the 2-dimensional boundary, is where the true laws reside. Not that the world is less real, but that its reality is built from rules hidden beneath our perception. The way music emerges from notes, or a storm from shifting air. And just as you don't need to see each molecule of water to feel the rain, you may not need to see the holographic substrate to be fully embedded in the cosmos. Some scientists believe this principle could help unify the competing theories of physics, marrying the smooth elegance of general relativity with the jittery, probabilistic nature of quantum mechanics. It could provide a way to describe black holes without paradoxes, to understand space-time not as a fixed arena, but as a construct that arises from information itself. There are even hints that the early universe, near the Big Bang, may have existed in fewer dimensions, that space itself unfolded over time, growing richer, thicker, more complex. This doesn't mean the world around you is fake, or that we live in some digital simulation. Instead, it offers a new language for understanding reality, one where depth is a consequence of entanglement, where locality is woven from relationships, and where the stage of the universe may be both more and less than it seems. If the holographic principle holds true in our cosmos, then the edge of everything, the farthest boundary of the universe, is not just a limit, but a library, a ledger of events, entangled and encoded, from which the richness of stars and silence and thought emerges. In that sense, we are not simply living inside the universe. We may be written on it. Before the universe began expanding, before light scattered or time flowed, there may have existed a reality stranger than anything we can picture. Not nothing, not emptiness, but a tangled storm of vibrating threads, infinitesimally small, vibrating in hidden dimensions, each one humming with the potential to become everything we would one day call the universe. This is the world suggested by string theory's vision of the pre-Big Bang, a landscape where the smallest scales held the deepest secrets, and where the fabric of reality was not yet stretched into the cosmos we see now, but folded tightly upon itself, resonating in silence. In string theory, particles are not tiny points, but rather one-dimensional objects, strings whose different vibrational modes give rise to the properties of matter and force. A string vibrating in one pattern might manifest as an electron, while another might appear as a graviton or quark. The universe, then, is not made from building blocks, but from music. Every particle is a note, every interaction a chord, and the melody is conducted through dimensions we do not see. To make the mathematics work, String theory requires more than the four dimensions we know: height, width, depth, and time. It suggests that there are 10 or even 11 dimensions, some of which are curled up so tightly they are invisible to us, like threads woven so densely into a fabric that they vanish from the eye, but remain essential to the pattern. In this hidden arena, before what we call the Big Bang, the universe might have existed in a high-energy state governed by the dynamics of strings. Instead of an exploding point of infinite density, the beginning might have been a transition between phases, a shift in how these strings were arranged, how they vibrated, how they interacted. The concept of a singular beginning dissolves into a story of unfolding geometries, a cosmic rearrangement within a multi-dimensional canvas. One model within string cosmology proposes that the universe once rested in a static or contracting state, not expanding, but curled inward, dense and hot, waiting. Space may have been filled with a form of exotic energy, not like the stars or atoms we know, but with something far more fundamental: dilatons, tachyons, and winding modes. These are not particles in the traditional sense, but expressions of how strings behave under intense constraints. Imagine strings wrapping around compact dimensions, coiling and binding space so tightly that it cannot grow. These winding modes resist expansion until something breaks their hold. When oppositely wound strings meet, they can annihilate, canceling each other out and releasing their energy. And when enough of this happens, the resistance lifts, the universe begins to stretch. A phase transition occurs, not unlike ice melting or water boiling, but on a scale that births galaxies. This transition is not necessarily smooth. In string theory, the universe could have passed through a moment where familiar space-time didn't exist in any conventional sense. A period governed not by the laws of general relativity, but by the rules of quantum gravity. In this liminal phase, the distinction between space and time may blur, the shapes of dimensions may shift, and the rules of cause and effect could bend in ways that feel almost mythical to us now. And yet, from this strange terrain, something recognizable emerged. As the universe began to expand, the temperature dropped, the energy scales fell, and the winding strings gave way to modes that allowed dimensions to stretch and matter to coalesce. The curled-up spaces remained hidden, but the large dimensions, the ones we inhabit, began to dominate. The seeds of structure, of stars and dust, were planted in this cooling breath, rooted in the quantum fluctuations of a string-filled past. In some versions of string cosmology, the Big Bang isn't a beginning but a bounce, a result of the collision between higher dimensional branes. These branes are vast surfaces that float in an even higher dimensional space, and our universe could be one such brane. When two of these collide, the energy unleashed could ignite a new era of expansion. The fire we call the Big Bang may be the aftershock of a much older event, a cosmic encounter between surfaces far beyond our perception. String theory doesn't just imagine what came before. It hints at the rules that shaped it. Dualities, deep symmetries in the mathematics suggest that what looks like a small space from one view may appear large from another. High energy may be indistinguishable from low energy under the right conditions. Time flowing forward may be mirrored by time flowing backward in another frame. In this view, what we call before may be a shadow of after, folded across a boundary we cannot cross. What existed before the Big Bang, then, may not be a question of when, but of how strings were arranged, how dimensions were shaped, how energy moved and transformed in a realm untouched by ordinary time. And in that realm, the silence before the song was not empty. It was vibrating. It held the hum of possibility, the shimmer of a universe preparing to bloom. Long after every star has gone out, long after the black holes have evaporated into a thin drizzle of radiation, and the universe is a dark, quiet stretch of nearly perfect uniformity, something strange may happen. Not a bang, not a crack or a flicker, but a transformation, a soft fading into something new, According to Roger Penrose's conformal cyclic cosmology, this isn't the end. It's not even the beginning. It's a transition from one universe to the next, a handoff between eons, where the vastness of one entire cosmos gives way to the birth of another. To understand this idea, we have to let go of a few assumptions. First, that the Big Bang was the beginning of everything. Second, that time has a hard edge, a singular start. And third, that what we call the end of the universe is truly a dead end. Penrose invites us to see the cosmos differently, not as a single arc, with a beginning and a heat-death finale, but as a repeating cycle, a succession of universes, each one expanding, aging, and dissolving into the conditions that allow the next to emerge. In this model, each universe, or aeon, as Penrose calls it, begins with a Big Bang and ends with an empty, exponentially expanding space. But something elegant happens at the end of each aeon. As the universe expands forever, all the structures within it are slowly erased. Stars burn out, matter thins, black holes evaporate, their mass fading into Hawking radiation over unimaginable time spans. What remains is pure geometry, a space that no longer contains mass, only radiation and expansion. This is key, because when mass disappears, scale stops mattering. Without mass, there's no way to measure size, no yardstick to say whether something is big or small. And here, Penrose makes a startling move. He proposes that the infinitely stretched out end of one universe can be mathematically transformed into the compact hot conditions of a new Big Bang. The edge of infinity in one eon becomes the beginning of time in the next, not by rewinding, but by remapping. It's like compressing a vast, flat desert into a single glowing point and finding, somehow, that the shape of the horizon matches the contours of the sunrise. It sounds almost poetic, but it's not just metaphor. The mathematics of conformal geometry allows for these transformations. It lets us squish and stretch space-time in such a way that the end of one universe can be smoothly joined to the beginning of another. Time, in this picture, doesn't run on a straight track. It loops forward through expansion, erasure, and rebirth, not as a return to the past, but as a continuation through fresh beginnings. And if this is true, Penrose argues, then we should be able to find fingerprints of the previous universe in our own. Subtle marks, ghosts in the sky. He and his collaborators believe they've found them: faint, circular patterns in the cosmic microwave background. The ancient light left over from the Big Bang. These circles, they say, may be echoes of massive collisions between black holes in a previous eon, the final fireworks of a dying universe. Their gravitational waves rippling through the conformal boundary and leaving an imprint in our sky. Not everyone agrees. The data is noisy, and cosmic microwave background measurements are notoriously difficult to interpret. Other scientists argue that these rings might be statistical flukes, artifacts of chance rather than clues from before time. But the idea has stirred debate, and with it, a sense of something larger, that our universe may not be alone in time, that the Big Bang was not a singular miracle, but one of many pulses in a grander rhythm. It's a rhythm we can't quite hear. Not yet, but Penrose's theory suggests it might be all around us, faint and stretched thin, like a song echoing across the walls of an ancient hall. Each note is a universe, swelling, resonating, then fading until only harmony remains. There is something haunting in this vision, not bleak, but solemn. It suggests that everything we know and are, from the laughter of children to the orbit of galaxies, is part of an ongoing procession. That time did not begin with us, that the silence before the Big Bang was not empty, but full of history, blurred into forgetfulness by the physics of transition. And maybe, far in the future, when our own universe has flattened into radiation and memory, some new cosmos will rise. It will not remember us, but perhaps it will carry the shape of us, faint and distorted, like a fingerprint pressed into the curtain of time. In that cosmos, a new sky will glow, a new chapter will begin, and somewhere, imperceptibly, our story will echo again. They slip through you by the trillions every second, unnoticed and untouched. Ghost particles, they're called neutrinos, born in the hearts of stars, in nuclear reactions, and in the quiet decay of radioactive elements. They travel at near the speed of light, without charge, with barely any mass, and they rarely ever interact with anything at all. They pass through planets as though they were mist. They are invisible messengers from some of the universe's most violent and ancient processes, and perhaps, just perhaps, they carry within them a memory, a whisper of something older than the universe itself. Neutrinos are only one kind of ghost, drifting silently through the cosmos. There are others. Gravitational waves ripple across the fabric of space-time, stretching and squeezing as they go. And then there is dark matter, the vast unseen substance that outweighs all the stars, yet reveals itself only through its pull on what we can see. None of these are easy to study. They are elusive, quiet, operating behind the scenes. But some physicists wonder, what if these strange phenomena are not just products of this universe, but survivors of a deeper past? What if they are fossils from before the Big Bang? If time had a beginning, then these particles and forces must have emerged shortly after. But if time is a loop or an illusion, or if the Big Bang was simply a phase change in a larger cosmic story, then some of these entities might carry signatures from beyond. They might have been shaped by conditions that existed before the cosmic curtain rose, still bearing subtle clues in their patterns, their energies, their interactions. A record not written in stone or light, but in movement and probability, an imprint encoded in the quiet. Take neutrinos. Of all the known particles, they are among the most mysterious. There are 3 known types: electron, muon, and tau, and they can morph into one another as they travel, a behavior known as oscillation. This property suggests that neutrinos have mass, though incredibly tiny, and that they do not quite fit neatly into the standard model of physics. Some theories propose that there may be a 4th kind of neutrino, a sterile one that does not interact even through the weak force. If such a particle exists, it could have been forged in the earliest moments of existence, or before, and it might carry with it patterns of symmetry or asymmetry that could point toward a pre-Big Bang physics. Then there are gravitational waves, first directly detected in 2015. They come from cataclysmic events, black holes merging, neutron stars colliding, but theoretically, they can also emerge from the deepest, oldest tremors of space-time itself. Some scientists have proposed the idea of a primordial gravitational wave. Background: a faint hum left over from the birth of the cosmos. These waves would not come from stars or galaxies, but from the quantum froth that may have existed when the universe was smaller than an atom, or, perhaps, from the collapse of structures in a previous aeon. Unlike light, gravitational waves are not scattered by matter. They pass through everything, pristine. If they exist, they could be the cleanest signal we have from before the universe became transparent. Detecting them is another matter. The instruments we have now, sensitive as they are, can only hear the loudest, most recent events. The deep, soft echoes of ancient gravitational waves would be many orders of magnitude quieter, like trying to hear a heartbeat beneath a thunderstorm. But the search continues. In quiet labs and frozen observatories, scientists listen. They tune their instruments like musical strings, hoping to catch the faintest rhythm of something older than stars. And then, there is dark matter, the silent majority. We don't know what it's made of. It doesn't shine, it doesn't absorb, it doesn't scatter light. But we see its hand everywhere, in the rotation of galaxies, in the bending of light from distant quasars, in the formation of cosmic structure. Dark matter, by its nature, is ancient. It does not decay, not in any way we can see. It may have formed in the first fractions of a second after the Big Bang, or it may have been there already, waiting. Some theories suggest that dark matter might not be made of particles at all, but of primordial black holes, remnants of high-density fluctuations from the earliest times. Others suggest axions, or supersymmetric particles, or other strange candidates that have never been seen in a lab. And if dark matter does carry echoes from before, it would be in how it's distributed, how it clumps, how it interacts or doesn't with the rest of the universe. These are not answers, but traces, faint, smudges on the glass. We look at the sky, at the data, and try to infer what these ghosts might be telling us. Some scientists use particle accelerators, some use satellite telescopes. Others write equations that stretch across chalkboards like incantations, and all of them, in one way or another, are listening for a message that might be older than time. There is a chance, small, perhaps, but real, that these ghost particles are not just a part of our universe's present, but messengers from a forgotten past, that their strange behaviors are not quirks, but codes, that somewhere in their spin, or their decay paths, or the way they curve through space, there lies a fingerprint of what came before. A universe can forget many things. Stars die, light fades, atoms drift apart, but neutrinos do not stop. Gravitational waves do not silence. Dark matter does not vanish. They go on, indifferent and eternal, like echoes in an endless cathedral. And if we can learn to read their language, we may yet discover that we have always been living in the shadow of something that came before, something vast, something silent, and something still speaking in a voice too quiet for ears but not for minds. Somewhere in the depths of space-time, beyond the swirl of galaxies and the stretch of cold, black void, a question lingers like a whisper through a dream. What if the universe is not just a stage for consciousness, but consciousness itself? Not merely a place where life happens to arise, but a being in its own right, not alive in the way we know life, but aware, responsive, evolving through thought instead of force. It's a fringe idea, to be sure, but fringe does not mean empty. It means daring. It means peering over the edge of what we call reality and wondering whether the mind is not a product of the universe, but its architect. The notion is as old as philosophy and as radical as quantum physics. In ancient traditions, consciousness was often seen as fundamental, not something brains produce, but something everything shares. The Vedas whispered it. Taoists hinted at it. Some early mystics imagined the cosmos not as dead matter set into motion, but as a kind of mind dreaming itself into form. Today, science doesn't speak in those terms. It deals in particles and equations, forces and fields. But lately, a few physicists and philosophers have begun asking if we've made a mistake by pushing the mind to the sidelines. Because the deeper we go into the fabric of reality, the stranger it gets. Matter isn't solid. It's mostly empty space, held together by forces that behave like probability more than clockwork. At the quantum level, particles seem to exist in multiple states at once, only choosing a position when observed. Some interpretations suggest that it's the act of observation awareness that gives rise to outcomes. That without an observer, the universe remains in a kind of blur, a soup of potential. Could that mean consciousness isn't just along for the ride? Could it be that consciousness carves the path? One idea, known as panpsychism, proposes that consciousness is not rare or emergent, but universal, that every particle, every quark, every atom contains a flicker of awareness, not like ours, not thinking or feeling in a human sense, but possessing a basic capacity to experience. From this perspective, a rock is not just a rock. It's a congregation of tiny awarenesses, bound by physics, but not devoid of presence. The difference between a human and a rock is not that one has consciousness and the other doesn't, but how that consciousness is arranged, how deeply it integrates and reflects. Other models go further. Integrated information theory tries to quantify consciousness, to assign a value to how interconnected and irreducible a system is. In this view, any structure that has enough complexity and internal feedback might be conscious to some degree. A brain scores high. A tree, perhaps lower. But what about the universe? Could the cosmos, with its billions of galaxies, its gravitational webs, its quantum entanglements spanning light years, be conscious in its totality, not in the way a person is, but in some unimaginable, expansive sense? Then there's the participatory anthropic principle, which suggests that consciousness and the universe are locked in a kind of feedback loop. The universe gives rise to conscious beings, who then, through observation, bring the universe into being. It sounds paradoxical, like a hall of mirrors reflecting itself into infinity, but at the heart of quantum mechanics, strange loops like this are not so easily dismissed. Some thinkers take it even further, suggesting that consciousness doesn't arise from the brain at all, that the brain is more like a receiver, tuning into consciousness the way a radio tunes into a signal. If that's true, then consciousness might be something woven into the structure of reality, like time or space or energy. Not an emergent property, but a foundation. Not a side effect, but a source. And from that idea blooms another, even stranger thought. What if everything we perceive, time, matter, the laws of physics, are not primary, but emergent from mind? That reality, as we experience it, is the result of a deeper level of information processing, not mechanical, but mental. Not a simulation in the digital sense, but a kind of dream, a projection, a thought thinking itself into complexity. This sounds like mysticism wearing a lab coat, and yet, the more we look, the more the boundary blurs. Information seems to be more fundamental than matter. Entropy, the flow of time, the very structure of black holes, all of it dances around information, not substance. Some physicists describe the universe as a vast quantum computer. Others speak of space-time itself as emerging from entangled information networks, like a tapestry woven from unseen threads. And what is information, if not the raw material of thought? We may never know for sure. Consciousness is the most intimate thing we experience, and yet the least understood. We can't measure it directly. We can't prove it exists outside ourselves. And yet, it's the only thing we can be absolutely sure of, that something is aware. Descartes said, "I think, therefore I am." But perhaps it's even simpler. Awareness is, before stars, before atoms, before equations, awareness. Maybe the universe is not a machine but a mind. Maybe it's not governed but growing, not engineered but imagining. And maybe, in some deep, recursive way, when we ask these questions, we are the universe asking itself, not as a metaphor, but as truth. At the edge of every question we ask about the universe, there waits a deeper one, older and quieter, like a shadow at the base of a flame. Why is there something rather than nothing? Not just how things began, or what existed before the Big Bang, or whether time loops, or stretches, or halts, but why existence exists at all, why anything is here, why we are here, wondering at all. It's a question so vast and so unsettling that most answers don't dare go near it. Physics can model the birth of space and time. Cosmology can track the unfolding of the universe in exquisite mathematical detail. But when you get to the root, when you ask why there is anything at all, the trail vanishes into silence. It's not just a scientific mystery, it's an ontological puzzle, a riddle about being itself. A question that slips between logic and intuition, like a dream that almost makes sense but evaporates when you try to describe it. We are so used to something, to air and ground and light and thought. But the alternative, a pure, total nothingness, is not just the absence of matter or light. It's the absence of laws, of structure, of possibility. No time ticking, no space spreading, no mathematics, no energy, No vacuum, not even emptiness, just non-existence. And yet, here we are. There are some who argue that this question is meaningless, that asking why there is something rather than nothing presupposes that nothing is somehow the default state, when maybe it isn't. Maybe something is inevitable. Maybe existence is the only game in town, and nothingness was never a viable option. Others say that the question is a linguistic illusion, that we're playing with words that point to concepts our minds weren't built to fully grasp, and that the contradiction only exists because we're trying to stuff too much meaning into a single sentence. But the question persists. It lingers in physics classrooms and late-night philosophy debates, in poems and prayers, and the quiet thoughts before sleep. Leibniz asked it in the 17th century. Heidegger asked it again in the 20th. And long before them, it echoed through ancient texts, not always in the same words, but always circling the same mystery. Why something? Why now? Why this? Some theories try to explain it with logic. One idea is the principle of sufficient reason, that everything must have a reason or cause. But that only kicks the question up a level. What caused the cause? What gave the first domino its push? If we say the universe came from a quantum fluctuation, then we have to ask where the quantum field came from. If we say it emerged from the laws of physics, we must then ask why those laws exist and not others or none at all. Other ideas suggest that perhaps everything that can exist does that reality, is a vast ensemble of all possible worlds, and we simply find ourselves in one of them, the way a fish finds itself in water. It's not special, just a fact of presence. In this view, nothingness isn't more natural or more probable than existence. It's just one possible state among many, and perhaps not even a stable one. Maybe nothing is like a vacuum too perfect to stay still, and the slightest ripple, the tiniest quantum itch, gives birth to a world. But even that explanation feels like a sleight of hand, because we're still left wondering where the possibility came from. Why is there a canvas that allows for anything to occur at all? Why is the stage there in the first place, with rules and probabilities and the capacity for events to arise? Some thinkers take a different route. They propose that the question itself is an ontological loop, a self-referencing structure, like a Mobius strip or a paradox. Asking, why is there something, assumes that there could be an answer that exists outside of existence. But if everything that can be is already part of being, then the question folds back in on itself. It's like trying to draw a circle with a beginning. The act of questioning presupposes the very thing you're questioning. And perhaps that's the clue. That existence doesn't come from anything else. It simply is, self-contained, self-justified, a fact without a frame. Still, some philosophers and scientists believe that consciousness, the very thing asking the question, might be central to the answer. If awareness is fundamental rather than emergent, then perhaps the universe exists because it is being observed, or because it is the observer itself. This loops us back to ideas from ancient mysticism and modern quantum theory alike, where the line between mind and matter dissolves, and the cosmos seems to gaze inward. There is also the unsettling thought that there may be no answer, that the why we keep returning to is a human craving projected onto a universe that operates without purpose or intention. We want stories, we want meaning, we want causes that comfort, and patterns that explain. But nature may not be in the business of comfort. It may simply unfold not for a reason, but because there is no alternative. And, yet, the question remains, floating just out of reach. It's not a problem to be solved, but a compass, pointing toward the edge of what thought can hold. It's a mirror we can't look away from, even if it shows us nothing but our own reflection. Perhaps that's the truth of it, that something exists because it must, or because it can't not, or because existence is not something that begins, but something that simply refuses to end. And in the silence between each thought, in the dark behind the stars, the question still waits. Not for an answer, but for the next person to ask it, Before equations carved the cosmos into symbols and telescopes stretched our gaze into the cradle of time, we looked up with eyes full of wonder and hearts full of story. We didn't speak of dark energy or singularities. We spoke of gods and beasts, of breath and fire, of chaos calmed by song. We didn't know about cosmic inflation, but we dreamed of beginnings in shapes we could carry, shapes we could pass down through voice and firelight. Before we asked what exploded, we asked what dreamed. To understand what ancient cultures thought about the beginning, you have to step sideways from the language of physics. You have to pause the ticking of atomic clocks and set aside the logic that divides fact from fiction. In their place, you listen for rhythm and metaphor, for what humans felt in the marrow of their being before words hardened into laws. In ancient Egypt, the universe began in still water. None, the dark primordial ocean, was not chaotic, but full of latent potential. From that silent vastness rose a mound like the first island breaking through a flood. Upon it emerged Atum, the first god, who created other gods by speaking or weeping or breathing. Creation in this telling wasn't violence, it was emergence. A slow revealing of order from stillness, light unfolding from depth, something born from what was always waiting. In Mesopotamia, the Babylonian myth of Enuma Elish told of a time when there was nothing but Apsu, the fresh waters, and Tiamat, the salty sea. From their mingling came gods, and from their conflict came cosmos. Tiamat, the great dragon of chaos, was torn apart by Marduk, the storm god. Her body became the heavens and the earth, her eyes, rivers, her tail, the Milky Way. Here, creation was struggle, a wrestling of order from the jaws of the formless. The universe was not given, it was taken, shaped by will and war. The Rig Veda, among the oldest sacred texts of India, speaks of a time when neither being nor non-being existed. A place where even darkness was wrapped in darkness. Desire arose first. It says desire, the seed of mind, and from mind, the cosmos stirred. There is no clear cause, only suggestion, creation as yearning, as a ripple in the void of pure potential. And then, in a whisper of humility, the hymn ends. Who really knows? Who will here proclaim it? Whence was it produced? Whence is this creation? Even the gods, it suggests, came later. Maybe even they don't know. In China, Taoist cosmology spoke of the Tao, the way, as the source of all things. Not a being, but a flowing. Not a god, but a principle. The Tao gave birth to one. One became two, yin and yang. Two became three. And from three, the 10,000 things. Here, creation is not a moment, but a movement, a breathing in and out, a dance of balance, ever unfolding. The world isn't made once, but remade in every moment as harmony shifts and cycles turn. The Norse imagined a great void called Ginnunga Gap, flanked by the realms of fire and ice. Where they met, the thawing dripped life into being. A giant, Ymir, was born, and from his flesh and blood, the world was built. His bones became mountains, his skull, the sky. In this myth, the cosmos is a body, and we live within its ribs and veins. Creation is sacrifice, the death of the first to give life to the rest. The Hopi people of North America tell of a series of worlds, each created and destroyed in turn. We live in the fourth world, birthed from the emergence of humans through a hollow reed from the underworld below. Life, to them, is migration, spiritual and literal. A slow, sacred climb. The beginning isn't a blast, but a breath. Not a bang, but a blooming. In Maori tradition, all things began in darkness. Te Kore, the nothingness, followed by Tepo, the night. From these came Ranginui, the Sky Father, and Papatuanuku, the Earth Mother. They clung together in a tight embrace, their children pressed between them. The gods, cramped in darkness, yearned for space, and so they pushed their parents apart, letting light flood in. The world was born from separation, light through sorrow, space through rupture. These myths do not contradict science. They don't try to. They speak a different language entirely, a language of soul rather than measurement. They ask not what happened, but what it means to be. They echo the deep intuition that before the world was visible, it was imagined that behind matter lies meaning, even if that meaning shifts from voice to voice. And perhaps, in the quiet turning of these stories, we catch a glimpse of something our equations sometimes miss. That the urge to explain the beginning is not just scientific, it's human. That awe predates the telescope. That myth, like music, reaches places numbers cannot. Not because it's literal, but because it's listening. And if you sit still enough, long enough, you might hear what they heard echoes in the silence before everything, calling us to remember not just how things began, but that they did, and that we are here, telling stories about it, stories full of gods, or breath, or dragons, or dreams, stories that reach not for certainty, but for belonging, for meaning in the mystery. And in that, perhaps, we are not so different from those who lived by starlight and fire long before we gave the beginning a name, in the stillness before sleep. Imagine this, a universe that never began, no explosion, no origin point, no birth cry echoing through the silence, just existence, steady and unbroken, like an eternal sea without a first wave. It's a concept that slips through the fingers of our understanding, because everything we know is framed by beginnings and endings. We are born, we grow, we die. Every book opens and closes. Every star, no matter how radiant, flickers into being and fades into dust. The idea that the universe itself might be exempt from this rhythm, that it might simply be, is a quiet, bewildering sort of awe. To say the universe never began is not to say it always looked the way it does now. The galaxies we see, the laws we measure, the particles we count, those may all be features of a chapter, not the book, but the canvas on which it's all painted, the foundational presence of reality itself, might have no starting line. It might be timeless in the truest sense, not eternal in the way a clock ticks forever, but eternal in the way a circle has no corner, no edge, no before. This idea has haunted philosophy for thousands of years. The ancient Greeks wondered if the cosmos might be ageless, cycling endlessly without need for divine intervention. The Stoics imagined a universe born in fire and ending in fire, again and again, each cycle identical, unfolding as fate demands. The concept was seductive, not just for its symmetry, but for its removal of arbitrary causes. If the universe had no beginning, it needed no creator. It simply was. Modern physics, armed with tools the ancients could never have imagined, has found itself circling back to that same profound possibility. Some models suggest that what we call the Big Bang wasn't the start of everything, but just a phase transition. Like water freezing into ice, the fabric of the universe may have crystallized from a prior state, one we don't yet understand, but which existed all the same. In these views, the Big Bang isn't a beginning, it's a change, a pivot, a veil pulled back, and beyond that veil, there may be no time as we know it, no ticking clock, no sequence of events. In quantum gravity and other theoretical frameworks, time could be emergent, not fundamental. What we call before might have no meaning in that domain. It's like asking what's north of the North Pole. The question feels sensible until you realize it rests on an assumption the universe doesn't share. Even stranger are the models that discard time altogether. Julian Barbour, a physicist and philosopher, has proposed that time is an illusion, a byproduct of the way we perceive change. In his Timeless Physics, the universe is a collection of moments, like snapshots scattered across a floor. We move through them like a needle threading a quilt, and our sense of past and future arises from the order we impose. But in truth, all moments simply are, coexisting, complete, no first, no last. What if the cosmos is like that? Not an arrow shooting forward from a spark, but a landscape, vast and unmoving, in which every peak and valley simply exists. In this view, the question, when did it begin, is like asking, when did a mountain start? It didn't. It just stands. Time, then, is the dream of the traveler, not the trail itself. There are still others who approach the same idea from a different direction. Some models of the multiverse suggest that the broader cosmos, the totality of all possible universes, has no origin point. It has always been bubbling, branching, blossoming. Our universe, with its Big Bang and its stars and its spiral galaxies, may be just one blossom in a field of infinite flowering. The field has no seed. It's just there, endless, self-existing. And while these ideas stretch the imagination, they solve a curious problem. If the universe did begin, we must ask why. Why then, and not before? Why from nothing, and not from something? But if there was no beginning, then perhaps there is no why. Or perhaps the why is built into the very structure of existence, like a melody that needs no composer, only a string to be plucked. It's a notion that can feel cold or comforting, depending on the heart that receives it. Some crave a spark, a divine gesture, a guiding hand. Others find peace in the idea of a universe that is not owed to anything, that rests on nothing but itself, like an infinite ocean without a shore. And maybe, if we let go of the need for origin stories, we can find beauty in simply being, in the way galaxies drift, in the silence between stars, in the knowledge that existence does not have to be explained to be felt, that there is wonder not only in beginnings, but in what has always been. So what if the universe never began? What if we are part of something that has no outside, no start, no final page? It would mean that we are not the result of a single flare in the darkness, but participants in a quiet, eternal unfolding. Not a story with a prologue, but a presence without parentheses, an isness that needs no origin to be profound. And in that endlessness, perhaps the deepest mystery is not how it started, but that it continues to hold us, night after night, as we drift through it, asking questions older than time,